All right, let's roll right on to Unit 3.2, Ionic Nomenclature. I had said yesterday something about your ability to learn another language by taking chemistry class, and this is where that all starts in Section 3.2, Ionic Nomenclature. So the first thing we got to talk about are something called oxidation numbers. So the oxidation numbers are going to help us answer this question. How do we know the ratio that elements actually combine with? So for instance, table salt. If you're working with table salt, you probably know that it's NaCl, sodium chloride. Okay, but if you're working with the stuff that we were working with in the lab, in the YouTube lab, which was copper chloride, that was CuCl2. Okay, there was a little 2 subscript. Okay, so you've got a lot of different options here. Aluminum oxide. Okay, aluminum oxide is actually Al2O3. So how do we know what these subscripts are on the bottom of these formulas? So that's what oxidation numbers are going to help us answer. These ratios are due to the element's oxidation number, and that's defined as the number of the charge an element would gain if it were to become stable. The number of the charge an element would gain if it were to become stable. So let's look at what elements have to do in order to become stable. I'm going to just bring up this chart, which should be familiar to you, and you're going to look at the first, let's see, 3 elements. That's lithium through boron. I'm gonna just kind of half circle them with my purple marker here. And you're going to notice that each one of these elements are going to want to jettison some electrons in order to become stable. So for instance, lithium's going to want to lose 1 electron. Beryllium will want to lose 2. And boron's going to want to lose 3. Now you might be asking, well, why don't they want to gain electrons? That's a pretty good question. Well, in order for lithium to gain electrons and become stable, it would have to not only fill up that 2s energy level, but it would also have to fill up the 2p. So that means it'd have to gain 7 total electrons. So you always want to ask yourself, what's going to be easier, losing 1 or gaining 7? Well, losing 1 is much, much easier. So we're just going to lose that guy right there. It's gone. If lithium loses 1 electron, the charge on lithium becomes 1 plus. Okay, let's talk about the next one then. Let's talk about beryllium. Same concept. Beryllium looks full, right? Because those 2 sublevels are full, but in actuality it's not, because we need electrons in the 2p as well in order for that second energy level to be full. So it's got an option. It can either lose 2 or it can gain 6, and in this case it's going to want to gain 6. I'm sorry, it's going to want to lose 2 electrons. All right, so when it jettisons those 2 electrons, it becomes 2 plus. And we can follow that same theme for boron. Boron will be 3 plus. Now carbon is the midpoint of this, because carbon has the opportunity to can either gain 4 electrons or lose 4 electrons. And that's what makes carbon so versatile. So we give it a 4 plus or minus. So it depends on what it bonds with, whether it's going to lose or gain those 4 electrons. And then once we get to carbon, now we have kind of jumped over to the other side. And the other elements, nitrogen, oxygen, fluorine, are actually going to want to gain electrons. Now, let's take a look at nitrogen first. So here are the outer shell electrons for nitrogen. There are 5 of them, 5 valence electrons. It can either lose all 5 of those, or it can gain 1, 2, 3. And if it gains 3, it's going to be stable, meaning it'll have the same electron configuration as neon down here. Okay, so gaining 3 is going to be an easier option. So it's going to gain 3 electrons, so it has a 3 negative charge. If you follow that same path, then oxygen is going to have a 2 negative charge and fluorine a 1 negative charge. So what we have just developed are the oxidation numbers for these, let's see, 3, 6, for these 7 elements. And we could actually do it for neon on the bottom down there. Neon's stable, so its oxidation number is actually 0. It's not going to want to gain or lose. So we know the oxidation numbers of 8 different elements. You might be asking, do we have to memorize the oxidation numbers for all 117? No, there's going to be a little trend that the periodic table will help us with, and we'll show you that right here. Alright, so let's go find lithium. There's lithium. And we said lithium's going to lose 1 electron. Well, if you write out the orbital diagram for all of the other elements inside a lithium's column, that's the group 1 alkali metals, you'll notice that they all want to lose 1 electron. And in that case, they're all going to be 1 plus. Beryllium was the second element that we looked at. It was 2+. And again, if you write out the orbital diagram for magnesium or calcium or strontium, again, you notice that they all want to lose 2 electrons. So their oxidation numbers are 2+. We're going to skip this middle section, and we'll find out in a second why that is. And we'll jump over to boron, and the boron column has oxidation numbers at 3+. And then comes carbon. Carbon was our midway point, right? And the option of gaining or losing 4 electrons, depending on what it bonds with. Okay, that's the carbon. And then if we jump over to the other side, then nitrogen starts the rows of elements that actually are going to gain electrons. So nitrogen will want to gain 3, oxygen's column will want to gain 2, and fluorine's column will want to gain just the 1. Okay, and then the alkali metals are going to be neutral, so we get a 0. Or I'm sorry, the noble gases are going to be neutral, so we put a 0 over the top of them. So really, if you're looking for like sulfur, what's the oxidation number for sulfur? Most of the time it's going to be 2 negative. And you can use that to help you write the formula for the compound. So we're going to see how to do that on the next couple of pages here. So the first type of compound we want to learn to write is called a type 1 compound. These are ionic compounds that contain a metal and a nonmetal. So NaCl is a very good example of that. So first of all, let's do the easy part, naming these things. You name the metal per usual, so Na is just sodium. And then you change the ending of the nonmetal to IDE. So instead of calling this sodium chlorine, we'd call it sodium chloride. So written out, it just looks like this, sodium and chloride. And that's it. That's really all there is to it. Now naming this thing is not the difficult part. Sometimes actually writing it is the difficult part. So what do these subscripts be in the formula itself? Well, sodium. This is where we go to the periodic table. Sodium has an oxidation number of 1+. We just wrote that over the top. Okay, and chlorine has an oxidation number of 1 negative. So if I crisscross those numbers, and this is important, this is kind of a little trick that we use. If you crisscross those numbers, instead of being superscripts, they're now subscripts. You actually would have, let me write this in a different color. You actually would have just Na1Cl1. But just to kind of save time, we don't have to write the ones. Just like in algebra, you don't write 1x, you just write x. So we do the same thing in chemistry. So we can just call that NaCl. So what that means is that for every 1 sodium atom, or 1 sodium ion, you have 1 chloride ion that can pair up with each other in that particular formula. And you don't have to worry about the pluses or the minuses as the subscripts at all. Alright, now at the end of the day too, you always want to make sure that your charges equal out. So I've got a 1 plus here and a 1 negative here, and I've got 1 of each. So I've got 1 plus and 1 negative, that equals a 0. Good, I've got a neutral compound. Those subscripts don't get mentioned in the name at all, so we don't call this like sodium 1 chloride 1. We just call it sodium chloride. Alright, so to do another example, if we were going to look at, let's say, magnesium chloride, magnesium from the table, it has a 2 plus charge. Chlorine has a 1 negative charge. Again, we'd go ahead and crisscross those numbers, and we'd come out with MgCl2. To make sure that that's correct mathematically, we've got 2 chlorines, and they both have a 1 negative charge. So if you multiply those together, you get a 2 negative, and that 2 negative cancels out the 2 positive to give you 0. So that works. So MgCl2 is magnesium chloride. All right. Let's go to type 2 compounds. We just have 2 left. Type 2 compounds a little bit more tricky because they include that middle section with the transition metals. Transition metals don't all have the same set of valence electrons because of their D subshell. So they don't have an exact oxidation number, unfortunately. So we don't always know what their charge is. So the charge has to actually be defined in the compound's name. So to do this, we always want to name the cation and anion just like type 1. So like iron chloride, for example, FeCl2 would just be iron chloride. But then we have to place a Roman numeral in between the ion names to specify the charge on the metal itself. So let me give you an example of how this one would work. Back up to a new page here. So before I talked iron chloride. So iron 2 chloride. So let's say that I gave you this and I said, hey guys, I want to know what the formula for that is. Well, iron is Fe and chlorine is Cl. And you know chlorine, you know the oxidation number for chlorine. It's 1 negative. Iron's in that middle section though, the transition metals, so you're not actually sure what the charge is. Well, that's what the Roman numeral is telling you. The 2 stands for 2 plus. So from here you just go ahead and crisscross the charges again and you'd get FeCl2. Now to go the opposite way, if I were to give you something like, oh, I don't know, copper oxide, CuO, copper oxide, and I wanted to know how do you say that? Well, you know Cu is copper, and you know O is oxygen, so you call that oxide. Okay. Now you need to know what that Roman numeral is. Well, there are no superscripts up there right now, so how do you figure those out? Well, what you do is you re-crisscross the charges. So just think about there being charges down there. So put one up there and up there. Well, there are no charges on the bottom, so your brain probably tells you that's got to be 1 negative and that's got to be 1 positive. But when you do that, hopefully you realize, wait a minute, oxygen's not 1 negative. Oxygen's actually 2 negative. So in order for the subscripts to cancel each other out, that means that the oxidation numbers of both the anion and cation had to be the same. So copper had to be 2 plus and oxygen had to be 2 minus. Then when you crisscross them, yeah, they still cancel out. Remember, it's a ratio. So that means that the Roman numeral for copper oxide is going to be 2, copper 2 oxide. That'll be your answer there. All right, and the last compound are the ones that contain both ionic and covalent bonds, and we'll talk covalent bonds a little bit later. But these compounds usually have, they look a little bit scary because they have more than 2 elements involved in them. The bond between the sodium and that big thing in parentheses is actually an ionic bond. There's a transfer of electrons that allows those 2 things to come together. And because the oxidation number on sodium is always 1 plus, in order for there to be no subscripts, then the oxidation number on that big thing must be 1 negative. But the bonds between the N and the O are covalent. Now, right now we are not going to concern ourselves with how the N is bonded to the O. That comes a little bit later. But these types of ions, when you've got more than 1 atom in the ion, have a special name. They're called polyatomic ions. That means many atoms per ion, polyatomic. And there is a Quizlet posted on Edmodo that has the 22 polyatomic ions that you have to know by heart for this class. Just to give you an idea of how they work though, if you have something like potassium sulfate, let me change colors here. Let's go with potassium sulfate. You'll notice that the ending of the cation is not "ide" anymore, it's "ate." That's going to alert you to go to your polyatomic ion chart and look for whatever sulfate is. You're going to find that sulfate is this guy. It's 1 sulfur and 4 oxygens that are combined together, and that whole species, that whole big beast, has a charge of 2 negative. Potassium, on the other hand, well, you should know that. That's just K. And its oxidation number is always 1 plus. And if we go ahead and crisscross those charges, okay, if we put the 1 down there and the 2 down there, well, then we should get a final answer of K2SO4 for potassium sulfate, K2SO4. Okay? So we're going to do a ton of practice with these things in class the next 3 or 4 days. All right, that's it.